And good afternoon, everyone. I am Subhajit Biswas from Material Chemistry Analysis Group, and I work a floor above the first floor in Kane Building. And today I'll talk about the growth and defect engineering in germanium nanowire in a bottom-up growth technique. So I've divided my talk into few parts. First, I will briefly introduce the nanowire structure. Next, I will come to the nanowire growth technique, mainly the catalytic bottom-up growth technique. Then I will come to our work, where we'll talk first about the growth kinetics control in a sub-eutectic or eutectic VLS-like growth technique. And then in the next part, we'll talk about the defect induction and defect control in the nanowire in a sub-eutectic growth technique. And also at the end, I will conclude with few important points from these two parts. So what are the nanowire? Nanowire are the structure where you have a very high length to diameter ratio. And these are the smallest actually nanostructure which can transport charge carriers. And it has a distinct density of states like these, then quantum dot or a thin film. And these are some nice example of the nanowire, indium phosphide nanowire, silicon nanowire grown vertically with gold seed. And they can be used in different aspect, different function, and they can be used for a nanowire transistor where they can be acted as a channel material or the interconnects, and you can put a gate all around the nanowire structure to have a wrap gate all around structure. You can have a nanowire solar cell where you can separate the charge at the junction, and then you can have a nanowire biosensor where the nanowire can act as a biomarker to capture your cancer cell or DNAs. And then you can also use nanowire for in vitro study. Oh, the bottom is actually down here. For the drug delivery into the cell. So what are the ways to grow nanowire? There are mainly two main approach. One is the top-down fabrication technique, and another is the bottom-up nanowire fabrication technique. In the top-down technique, you usually take a bulk of the material, then you design your mask or nanomask on top of it with different approach. That could be your E-beam lithography, could be a BCP lithography, could be nanosphere lithography, could be MAE, different technique. And this is one example of BCP lithography. And then with that nanomask, you can etch the bulk of the substrate to have your nanostructure on your device or on your platform of bulk. So here the good thing is that you can have nanowire of very high quality, and also you can grow nanowire or fabricate nanowire itself on the device platform. And these are the two examples. One is the PSPO nanomask on a silicon substrate, and this one is the silicon nanowire actually fabricated through EBL and HSQ resist with contact pad on SOI wafer. And then, but here we'll mainly talk about the bottom-up nanowire fabrication, where you nucleate your material, then you do the subsequent crystal growth. But while doing the crystal growth, you try to actually confine your lateral growth and have your longitudinal growth. And for that, you can do different technique. You can use inorganic templates like AO, or you can use organic templates like PVP or ethylene diamine. Or you can use a catalyst like a metal catalyst which can guide your unidirectional growth like this. But the good thing here with bottom-up growth that it will not give you the best quality nanowire like the top-down maybe. That could be kind of contradictory. But it will give you the opportunity to play around with morphology, to the structure, to chemical composition and different things. So you can have infinite kind of material in your repertoire. So here are the few examples of different kind of material you can have with bottom-up growth. This is one of the heterostructure, a superlattice kind of structure where you can have two different material one by one. You can arrange them to have different heterostructure. You can have even a simple axial PN junction, a simple radial PN junction, or a core shell nanowire. You can etch the core out to have your tube-like kind of nanowire structure or nanotube-like structure. But the first report of any growth with the catalytic bottom-up growth actually was reported way back in 1964, but not for the nanowire, but only for the micro whisker, and by Wagner in 1960 in a PL paper. And there they used the gold catalyst to grow this silicon whisker on a silicon 111 plane. But then from there on, the first reports of the nanowire structure came in late 80s or early 90s. This is one of the example of very early report of indium arsenide nanowire with gold catalyst, and you can see here the poor quality of the nanowire. They're not so great in those time. And this was one of the first example of direct observation of the nanowire growth inside a TEM in JACS published in 2001 actually. And here you can see from the gold catalyst how the silicon nanowire actually protrude, the coming out from the gold catalyst. But from here on, we have come a long way now. Now you can grow nanowire very precisely on a certain position with a certain pitch, with certain diameter, certain length, everything you can control very, very easily. And even you can put this nanowire in fancy devices like quantum computing devices, or now recent paper came out here in PNAS. Actually, they made a full logic circuit from a bottom of nanowire where they used a technique called nanocombing technique, where they can put the nanowire in a pre-aligned position and then they can put circuitry. So with bottom up nanowire, we have scope now to go further. So why we choose germanium in our case study? There are a lot of reasons, but the main important thing for us actually is this one on the red, that germanium is an elemental semiconductor and with a favorable growth kinetics than silicon. That means that germanium is suitable for different growth engineering. That could be other point, but we are more interested in this thing actually. So that's why, because if you take indium phosphide or gallium nitride, then your phase diagram and everything will be more complicated. So we choose this elemental part, germanium, as our case study, because then the explanation could be much more easier actually than a compound semiconductor. So to explain the bottom up growth, we can take the help of a binary phase diagram. Say for example, when you have this gold germanium system, the germanium nanowire growing from a gold catalyst, then you can start with a gold nanoparticle. Then with a certain uptake of germanium, you form this metastable eutectic liquid in this region. And from here on, when you reach the equilibrium concentration, then you have this one-dimensional growth of germanium coming out from the one end. And the growth could be two different kinds depending on what temperature you are in and depending on the eutectic temperature here. So if you are above the eutectic temperature, then your growth is driven by this mechanism. It is called a VLS-like growth model. But if you are below the growth eutectic temperature, then your growth is driven by a different mechanism where your catalyst will remain in a solid form throughout, and your growth is driven by the solid solubility and diffusivity here actually. And you will have a growth where your catalyst will be faceted, and it's called VSS-like growth model, vapor solid solid. And I have a nice video actually borrowed from internet. Oh, here, where the growth actually of silicon nanowire from a gold catalyst is shown here. You start with the gold catalyst on a silicon plane, and then you use this silicon precursor disilane, and with the capture of silicon in the catalyst, you can see the eutectic melting and the formation of this metastable eutectic AuSi alloy here in this region now. And then with certain uptake here, you will have a nanowire growth coming out from the one side of the nanoparticle. Okay. So with this, we can come to our work, where first we will talk about the growth kinetics control in a VLS-like growth model. So here you can divide the nanowire growth into four different parts. The first is the decomposition of your precursor, number one. Number two is the incorporation and the of the source into the catalyst. Number three is the diffusion and the solubility inside the catalyst here. And number four is the crystallization at the interface, or precipitation of your material at this boundary. And when you have very low amount of your precursor, then usually your growth is driven by this number 4 rate. This is the rate limiting step actually. And here the important criteria or important parameter is called supersaturation, which is the chemical potential difference of your material between vapor and the solid phase. So this actually drives the growth from here to here. And then this slide has a lot of equation, but it actually shows how this delta mu controls the growth kinetics. The growth kinetics can be divided into two parts, nucleation and the crystal growth rate. But in both scenario, if you take this and this into account, so for a bulk or for a nanoscale system, the nucleation will depend on delta mu. If you reduce or increase the delta mu, then you will reduce the induction time for growth. And even in this case also, for a bulk or for a nanoscale system, if you increase this delta mu value, then you increase the growth rate also. So, but then the question is that how to increase this delta mu for our system. Here for our system we got a very innovative approach actually, where if you consider this catalyst as a liquid solution of gold and germanium, then you can write the concentration of germanium in terms of this delta mu and this equilibrium concentration. And here in this equation, now if you reduce this Ce value by keeping C and T and everything constant, then you can increase this delta mu. But you can increase the delta mu even by increasing the actual concentration of germanium. But the problem is that here, if you increase C too much, then you have a lot of sidewall growth here, and you have a non-uniform nanowire diameter. So the best thing is that to decrease the Ce value to increase delta mu. But how to decrease this Ce value in our case? So for that actually, we took this approach where first this black phase diagram, this is a gold germanium phase diagram. So if you take a gold germanium system and if you consider a good temperature of 465 degrees centigrade, then if you now introduce 25% silver into that system, then suddenly you decrease this equilibrium concentration from 40 to 22%, and that should reflect in this delta mu value and in your growth rate. And with that goal into mind, we tried 3 different catalysts. One is gold, one is this 90 and 10 gold silver ratio catalyst alloy, and one is gold silver with 80-20 ratio. And all 3 catalysts give very nice nanowire. You can see they are very uniform in diameter, and also there's no particulate or homogeneous clustering in the sample. But the interesting thing to look is that for this gold silver 80-20 seed, the nanowires are much longer than pure gold seed and this 90-10 seed. And when you plot this growth rate distribution, you can see that almost 4 times increase in the growth rate for this seed than this seed, than a pure gold seed. So you have a fast growth kinetics with this gold silver seed than a pure gold seed. Now, if you consider the liquidous curve, the germanium liquidous for this 3 system, you can see a decrease in Ce value, the equilibrium concentration value, from 37 to 23%, and that is actually the reason we think for behind this increase in the length scale of the nanowire. So now, if you increase the growth time to 150 minutes with this 80-20 seed, you can have very long nanowire even on the millimeter length scale. You can see from this photograph the nanowire bundles, they are taller even than a euro cent coin. So, but the problem is now that while considering a nanoscale system, you can't consider growth rate alone. You have to consider the diameter effect also, because for nanoscale system, the Gibbs energy not only depends on the bulk value, also on the surface term also. So your chemical potential will be like this for nanoscale system, and the growth rate will depend on the diameter also. So when we compare the growth rate for these 3 different systems, we should compare for a similar diameter range, otherwise you can't conclude. So that's why we plotted this growth rate in terms of diameter for all these 6 different systems, and they all follow this supersaturation limited model. You can see that this actually follow a quadratic kind of a scale. And also you can see, if you consider now one single diameter, say 50 nanometer, you can see almost an increase of 4 to 5 times in the growth rate with this seed than this gold seed. Now we tried to plot this root V versus 1 by d actually here and here, and saw a linear curve, and from the intercept of this x-axis on the d value, you can find the diameter where your growth rate will terminate. That is called the critical diameter. And interestingly is that for the gold silver seed, the critical diameter is much kind of smaller than your gold seed. That means theoretically, if you can confine the surface diffusion of your particle, you can have much smaller nanowire with the gold silver seed than a pure gold seed, but theoretically. So now, further to confirm that fact that this equilibrium concentration is playing important role in determining this growth rate, we did some in situ TM experiment where we took our nanowire and put in the TM and heated at high temperature of 450 degrees centigrade. I have a video here also where you can see how the nanowire, actually the nanoparticle tip actually uptake the germanium from the nanowire and melt and expand and form this eutectic metastable liquid at the tip. And from this expansion of the catalyst, actually you can find the value of the Cg, the germanium equilibrium concentration, and we found for all these three different systems, and we have tried to plot the liquidias, the germanium liquidias curve for three different systems of different dimension. And this green thick line is the liquidias for the gold germanium bulk. But now we can see that for the nanoscale, the nano dimension, and also for different composition, you can see the shift of this liquidias either right or left of the bulk. And the important thing to note here is that the system with furthest right side have a slower growth kinetic system. So when you have high G concentration, then you have a slow growth kinetic system, the equilibrium concentration. And when you have a kind of a smaller G concentration, then you have a faster growth kinetic system. So you can relate the position of this nanoscale liquidias with the nanowire growth kinetics. So this slide, actually I will skip few slides here. Actually what we did, we tried to relate the growth kinetics with the interface morphology also, and but I will skip this because I think I don't have time for all this. I have another part actually, so I will skip these 2-3 slides where I think maybe we'll go directly to this area where we try to induce and control defects in nanowire in a subeutectic growth. So here, what's the motivation behind putting defects in nanowire? Here mainly we have put defects in the form of twin boundaries, where twin boundaries, they are the atomic plane which separate two mirror crystals. Say for example, for a cubic structure, you have a ABC arrangement usually, but now if you introduce a twin boundary here, then instead of ABC, you have a ABC and a mirror CBA arrangement. So these twin boundaries can be grown in nanowire in either in axial direction, where the twin boundaries are along the nanowire length, or could be grown kind of perpendicular to the nanowire growth axis, where the twin boundaries are like this. Usually for germanium or silicon nanowire, in this case the nanowires are grown along 112, and in this case they are grown along 111. And the thing is that if you can control this twin boundary formation, you can control the strain and stress in the nanowire, hence the band structure. Also interestingly, you can control the thermal conductivity and also the thermoelectric property. Another thing is that if you can control the formation of this twin boundary in a sequence, then you can form the pseudo-hexagonal region in the nanowire, and you can have this quantum dot-like structure. They are called crystal phase quantum dot. And also in another case, if you arrange the twin boundary in certain way, then you can form a lot of mini bands near the valence or conduction band edge, and you can have a direct transition of your carrier in an indirect band of semiconductor like germanium. So with all this motivation, we tried to put twin boundaries in the nanowire, and we actually used a very innovative technique where we tried to induce a lot of twin boundaries in the catalyst itself, and then try to transfer those twin boundaries in the nanowire body. And for this we use the subeutectic growth. So here we are not here, we are only here in this region, and for that reason we use three different catalyst sheet. One is pure silver, and another two are silver rich gold silver, 3:1 and 1:1 ratio. The reason is that because with these three sheet you lift up the eutectic temperature, and then with your growth temperature you are always below the eutectic temperature, and you follow a VSS like growth instead of a VLS like growth. And there are some criteria which actually need to follow to have this twin transfer process. These are listed here. So say for example, when we took silver as our growth catalyst, we got very nice nanowire, and even with the alloy sheet we got very nice nanowire. But the interesting thing happened when we took them to TM actually. So in TM they show a very nice this kind of epitaxial transfer process from the catalyst sheet to the nanowire body. You can see in this picture the alignment of your twin boundaries in the nanowire body and in the nanoparticle are almost similar. And also here the twin boundaries, they grow all along the nanowire length throughout almost micron region. And the effect here actually is very clearly shows the formation of twin boundaries. And also in this high-res image you can see the segment length of twin and non-twin segment in catalyst and in the nanowire is almost similar. So that actually confirms the fact that epitaxial transfer process is happening here for this twin transfer. And what we did, we tried to manipulate the twin density in the nanowire by changing the twin formation probability in the nanoparticle catalyst itself. So for that, we used these three different seeds, and with these three different seeds, you have different probability of twin formation because they have different twinning energy, and also they have different surface diffusion kinetics also. So for this reason, we got different amount of twin density in the nanowire sample with different kind of catalyst seed, and the maximum number of twin planes happen to be for these 3:1 catalyst. And so you can say that you can manipulate the kind of defect density in the nanowire. Our next goal will be, say, to manipulate the individual nanowire with this kind of twin formation of different density in the nanoparticle catalyst. So next, what we did, we tried to induce these twin boundaries perpendicular to the nanowire growth axis. This is more difficult because, say, if you take a conventional gold or a silver catalyst, they are for silicon and germanium nanowire. This kind of twin are not permitted actually because they are the weighting of the sidewall, the weighting of the catalyst with the sidewall here doesn't permit this kind of angle fluctuation. So you need a different kind of catalyst for this kind of twin formation in the nanowire. And here we use this magnetite iron oxide catalyst, where we use this block copolymer pattern nanodot with a hemispherical kind of shape. And here the growth is driven by this phase diagram, is complicated phase diagram, where you form different germanites, and with very, very high solubility of germanium, then only you have this germanium nanowire growth here. And here we also got very nice nanowire, and the nanowire tip actually confirm the formation of FeGe2 phase. But interesting thing happen again when you put them into TEM, and you can see this brightness contrast pattern in the nanowire along the perpendicular to the nanowire growth axis here, and they look like the computer barcode actually. But when you take them to high res mode, you can see this kind of formation of twin boundaries here or here or here, and you can see that the normal 3C arrangement, they are mirrored here along this twin plane, and also the normal 112 side facets for this nanowire, they are divided into two 111 low energy side facets. So we can have very nice twin boundaries in the nanowire like this with this innovative magnetite iron oxide seed. And we also have a diameter dependence on the density of twin boundaries, where for the thicker nanowire, the twin density are much more higher than the thinner nanowire, and we think it's something to do with this sidewall relaxation actually. For the thinner nanowire, it's easy to release the strain at the interface, and for thicker nanowire, it's not that easy. That's why you form more and more twin boundaries. And more interestingly, in certain sequence of twin here, they forming this pseudo-hexagonal phase inside a 3C cubic germanium lattice. Here in this case, actually you can see that in this and this region, which is the expanded region, there is a formation of this 4H arrangement of your lattice actually, and that will make a pseudo-hexagonal structure and a quantum dot-like structure, because your band structure is different in this two region than this region. And we are now trying to do a kind of localized yields to have the kind of exact band structure from this and this region. And so your arrangement actually changed from ABC to ABCB here in this and this structure. So, and we further confirm the fact that we formed this 4H region from Raman spectroscopy on a single nanowire, and we saw this extra peak of 4H GE peak here. So with this I will conclude actually. I will conclude with few important points. The first, we can say that we have found a new catalyst which can be more efficient than a conventional gold catalyst for silicon or germanium nanowire growth. We can't say for 3.5 at the moment, because we have to do more work on that. And then you can say that for this gold silver catalyst, you can reduce the critical diameter. That means if you can confine the surface diffusion, you can have much thinner nanowire with the gold silver. And also we have proposed this, we have drawn this nanoscale liquidius for this ternary system and tried to relate that with the growth kinetics. And for the subeutectic growth, we tried to induce a lot of twin boundaries epitaxially from the nanoparticle catalyst. And also we tried to induce twin boundaries perpendicular to the nanowire growth axis which can take us towards this twinning superlattice or a crystal phase superlattice structure. So with that, I will conclude and end, and I will thank all the members of MCAG group for all their help and for